SwayamPrabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. Last class we started deriving the rectangular plate PDE using just force balance, and we had completed deriving the moment resultants and shear force resultants, and I said I will show you these resultants on a differential element. Okay. So we have I can take it bigger actually, so let me do that. This is my midplane. This is X, that is my Y, and that is Z. Okay. So on the Y face we'll have MYY moment. This is MYY. Okay. On the other face we'll have the incremented moment, because that's a positive direction. So we'll have MYY plus del MYY by del Y dy. Then on the X we have MXX, and on the positive side MXX plus del MXX by del X dx. Okay, so this is dx and that is dy, let's say. Okay, now what else? We have the shear force resultant QYZ and QYZ plus del QYZ by del, let me write it properly. So we have QYZ plus del of QYZ by del Y dy. Okay, that is this one. Then on the other faces we have QXZ, and here the incremented shear force resultant, which is QXZ plus del QXZ by del X dx. Okay. Now what is left is the shear moment resultants. Okay. So on this face we'll have this way these are the x phases. So I have mx y mxy plus del mxy by del x dx. Then lastly we have myx and the incremented version myx plus del myx by del y dy. Okay, for pure bending, that is all we have. Okay, and now in league with Euler-Bernoulli and Kirchhoff theory, the rotational inertia is neglected, and therefore the moment equations are just static moment balances. So what do we get if I take the first equation? If I take this moment to be positive, okay, so what do I get? I get what do I get? I get mxy, okay, mxy plus, okay, we are taking first about the x axis. So mxy plus del mxy by del x dx, that is the resultant, into dy, that is the full moment, minus an my minus mxy into dy. Okay, so this has been taken care of, that has been taken care of. Now the only other contribution, okay, is from the shear forces. Okay, so that is now in the opposite direction. So I get a minus qyz. Okay, so there is an incremented version, but that will not contribute. So I will do straight away qyz into dx, which is the full force, okay, into dy, which is the moment. Okay, that is equal to 0. No, there is one more moment. Okay, there is one more moment, which is myy. Okay, so I have minus myy into dx. This one is also about x axis, minus myy dx plus myy plus del myy by del y dy, that is the resultant, into dx, that is equal to 0. Okay, now we have all terms. So if we cancel the common ones, this cancels with that and this cancels with that, what we get finally is qyz is equal to del myy by del y plus del mxy by del x. Okay, so that's a moment balance equation. Similarly, if you balance moments about y axis, you get qxz is equal to del mxx by del x plus del myx by del y. So these are the two moment balance equations. Lastly, we balance forces in the vertical direction. So what do we get? We get minus qyz into dx, the full force now, plus qyz plus del qyz by del y dy, the other side shear force resultant, into dx, the full force, then minus qxz dy plus qxz plus del qxz by del x dx dy. So this is the sum of all the forces in the vertical direction. Okay, so that is equal to, it's a full force, density into dx into dy into the thickness into del 2 w del t square, acceleration. Again this goes with that, this goes with that, we are left with del qyz by del y plus del qxz by del x is equal to rho h del 2 w by del t square. Okay. Now we have already found qyz, qxz in terms of moments. Okay. So if we substitute these moments, what do we get? We get del 2 myy del y square plus del 2 mxx by del x square plus del 2 mxy del y del x plus del 2 myx, both are equal but yx by del x del y, that is equal to rho h del 2 w del t square. Okay. Now to recall, mxx is equal to minus d del 2 w del x square plus mu del 2 w del y square, myy is equal to minus d del 2 w del y square plus mu del 2 w del x square, and mxy is equal to minus d1 minus mu del 2 w del x del y. Okay. If we substitute these, what do we get? We get minus a d del 2 del y square, okay, del 2 w del y square plus mu del 2 w del x square plus twice del 2 del x del y minus d into 1 minus mu del 2 w del x del y plus d del 2 del x square, or we'll put it minus right away, minus del 2w del x square plus mu del 2w del y square. Okay, this is equal to rho h w double dot. Okay, so this now results in d del 4w del x4 plus twice del 4w del x square del y square plus del 4w del y4 plus rho h w double dot is equal to 0. There is no forcing. Okay, so that's how you get the plate equation from force balance. Okay, now with this I close one thought process, which is we started with curves, then tangents and normals, tangents, normals. Then we went ahead and looked at curvatures, and we needed some relations like the Gauss-Kodazzi relations. Okay. Then we described a general point on a surface, and then a point within the material, alpha 1, alpha 2, alpha 3, and we went ahead and found the differential and the differential undeformed length, and then the deformed length, and then the strains and stresses, and then Love's assumptions, and finally Hamilton's law. And we arrived at the 5 equations, 5 general equations, in which if you substitute A1, A2, R1, R2, then you will get the exact equation for that particular surface. And when it came to curved surfaces, we said we will stick with surfaces of revolution. Okay, so that section I have come to a close with this plate equation. Okay, now what is the direction I am going to take from here? Once you have the equations, okay, say if you have equation of motion for a beam or for a rectangular plate or for a circular plate or a ring, let us say vibrating ring, or a vibrating cylinder or a sphere or any other relevant surface, we want the force response. Force response. If I force this structure, what is the response? Okay. In order to do that, our approach is we will need the resonance frequencies and the mode shapes. So we are going to use the modal summation approach. Okay, so we need to find the mode shapes. Okay, once you have the mode shapes, you can find the resonances. Once these two important modal parameters are known, we can go ahead and find the forced response. So we are going to look at resonances and mode shapes for a number of systems now, before going to the force response. And in places I will show you the mode shape animations. In MATLAB. Okay, many of you are not familiar with even lumped vibrations, because that is actually an elective still in most colleges. So I'll make an attempt to show you how modes look like. Okay, that will be very useful. So now along these lines, the first system that we are going to look at is the Euler-Bernoulli beam. Euler-Bernoulli beam. It is a one-dimensional structure. Okay, you can derive this also from the general system of equations. Okay, you will use the third and the fourth and the fifth equations and set all derivatives with respect to y to 0. Okay, then you will get this 1D Euler-Bernoulli beam equation. And how does it look like? It looks like E BH cube by 12 del 4 U3 by del x4 plus rho A being the cross section area, del 2 U3 by del T square, that is equal to 0. Okay, this is mass per unit length, and therefore we will call it rho dash, and this we will denote it as EI. Okay, now when we want to find the mode shapes, mode shape is a possible shape in which the structure can vibrate. Okay, where if it is initially deformed into the mode shape, and let go, that is the initial condition. Okay, and let go, then every point on the structure, or of the structure vibrates at the same frequency. Okay, what do I mean? For a simply supported beam, okay, this happens to be one of the mode shapes. This shape will be a mode shape. So if I manage to pull the beam in this shape in the beginning and I let it go, then it will start vibrating, okay, because it is away from the mean position, and every point vibrates at the same frequency. Same single frequency. Okay, if it is not the mode shape, it won't happen. Okay, this will happen, every point vibrates at the same single frequency only if it is a mode shape. otherwise multiple frequencies will appear, okay, under free vibration. Okay. So now how do we find the mode shape? So we will look for a harmonic response under free conditions. Okay. So what we will do is you will substitute for u3 some function of space e to the power of j omega t. Okay. So we are looking at a shape that vibrates at some omega. So if you substitute it back, what do I get? I get d4 this big u3x by dx4 minus lambda fourth u3 equal to 0. Okay. Where what is lambda fourth? Lambda fourth is this term omega square rho dash by ei. Okay. So this is the fourth order equation, ODE. Because it's an ODE, in the textbook the author takes a Laplace transform. Laplace transform. There are other ways of doing it, but as I have taken up the task of sticking with one textbook, I will do it that way. So it takes the Laplace transform. So Laplace transform, many of you are familiar. If I take a Laplace transform of this, what do I get? I get s fourth minus lambda fourth Laplace transform of u3 minus all the orders of s along with the boundary condition or initial condition s3 or s cube u3 of 0 minus s square du3 by dx at 0, all of these will be at 0, okay, minus s d2. We are used to taking Laplace transform for temporal equations. Now this is a special equation, okay, minus d3 u3, and hence all conditions are at 0, which happens to be x equal to 0. So if we now pull out u3 of s, we get 1 over s4 minus lambda 4 s cube u3 0 plus s square du3 by dx at 0 plus s d2 u3 by dx square at 0 plus d3 u3 by dx cube at 0. Okay. Now one should be able to take the inverse Laplace transform of this. Okay. So this is, you can do it from the tables straight away. So the u3 of x, the inverse transform looks like this: u3 of 0 a of lambda x plus 1 by lambda du3 by dx at 0 into b of lambda x plus 1 by lambda square d2 u3 by dx square 0 C of lambda x plus 1 by lambda cube d3 u3 by dx cube at 0 into t of lambda x. Okay, where I am straight away taking it from Sorel's book. Okay, a of lambda x is given by a half cos hyperbolic lambda x plus cos lambda x b lambda x is equal to 1/2 sin hyperbolic lambda x plus sin lambda x C of lambda x is 1/2 cos hyperbolic lambda x minus cos lambda x, then d of lambda x is equal to 1/2 sin hyperbolic lambda x minus sin lambda x. Okay, we will give some properties of this thing. You can see that a of 0 is 1, okay, whereas b of 0 is equal to c of 0 is equal to d of 0 is equal to 0. Okay, so we will continue along these lines. Time has run out, so I will see you in the next class. Thanks.